Today, we're going on an incredible journey. Not to outer space, but to inner space. We're going to see how scientists are mapping the hidden universe inside every single one of us, the microscopic machinery that literally makes us who we are. So, let's start with a really big question. You've got trillions of tiny little engines inside you right now doing absolutely everything, but they're totally invisible. So how in the world do we actually watch them work? How do we see what's going on in there?
Well, it turns out those engines, they're proteins. And the amazing technology that lets us see them is called mass spectrometry. Now, the best way to wrap your head around this is to think of it like a giant, super sophisticated racetrack for molecules. We're literally going to make these proteins race against each other to figure out who they are.
And here's the game plan for the race, the whole process in a nutshell. First, all the molecules got to get charged up. Then they get sorted out in the main event. After that, we take a closer look to get a positive ID. And finally, we snap a picture of the results. Simple as that. So, first things first, let's head to the starting gate. Because before any race can even begin, every single one of these molecules needs what I like to call a ticket to ride. Without it, they're not even allowed on the track. So, what is this ticket? It's an electrical charge. The fancy science term is ionization, and believe me, this is the absolute most critical first step. See, by giving a neutral molecule a little electrical zap, a positive or negative charge, we give the powerful magnetic fields inside the machine a handle to grab onto and fling it down the racetrack.
Okay, so there isn't just one ticket booth at this racetrack. Scientists have two main ways of getting these molecules charged up: ESI and MALDI. You can think of them as two different entrance gates, and each one is designed for a different kind of racer. And choosing the right gate is really important. ESI, which stands for electrospray ionization, is your go-to when your proteins are already hanging out in a liquid. But MALDI, now that's for when your sample is a solid. You actually embed it in a crystal matrix, zap it with a laser, and boom, the molecules are charged and flying.
All right, our molecules have their tickets, they're all charged up, and they are ready to go. So now, we get to the main event. This is the race itself, where millions of these molecules are about to get sorted. Now, this is super important. The race doesn't sort by just speed or size alone. It sorts by something called the mass-to-charge ratio. The best way to think about it is this. Imagine you're sorting racers based on how heavy they are compared to the value of the ticket they're holding. A tiny, lightweight molecule with a single charge is going to fly down the track very differently than a huge, heavy one holding that exact same charge. And just like in NASCAR or Formula One, there's not just one kind of racetrack. You've got different tracks for different kinds of races. So let's check out a few of them, starting with a real classic, the time of flight analyzer, or TOF. A TOF analyzer is probably the easiest one to picture. It's basically a molecular drag race. All the charged molecules get the exact same push, the same kick of energy, and they just fly down a long, straight, empty tube. And you guessed it, just like in a drag race, the lighter ones are faster. They hit the finish line, the detector, first. It's that simple and incredibly effective. But sometimes raw speed isn't what you're after. Sometimes you need pinpoint precision. And for that, scientists turn to other kinds of tracks, like the absolutely amazing Orbitrap analyzer. This is not a simple drag strip. Oh no, this is much more elegant. So let's quickly compare these racetracks. You've got the TOF, our straight-line drag race, fantastic for speed and for really big molecules. Then you have the Orbitrap, which traps ions in a perfect orbit around an electrode. The machine listens to the frequency they orbit at, which tells it their mass with just unbelievable resolution. It's like taking a super high-definition photo. And then there's the Quadrupole. It acts less like a racetrack and more like a bouncer at a club, using electric fields to let only very specific molecules get through. Okay, so we've run the first race, we've sorted all our molecules by their mass, awesome, but there's a problem. That only tells us how heavy they are. It doesn't tell us who they are. For that, we got to send them around for a second lap. Yeah, this is the next big question, right? Knowing the mass of a protein is like knowing the weight of a car in a race. It's good information. But is it a Ford? A Ferrari? Who's driving it? To find that out, we need a special technique called tandem mass spectroscopy, or MSMS for short. And here's the genius part. It works in 3 simple steps. First, we use something like that quadrupole bouncer to pick out just one type of racer from the thousands flying by. Step 2, We smash it. We hit that isolated molecule with a neutral gas, which makes it shatter into smaller, predictable pieces. And finally, step 3, we analyze those little pieces. That pattern of fragments is like a unique fingerprint. A computer can look at it and say, aha, I know exactly what the original protein was. It's like taking a car apart and identifying it just by looking at the engine parts. The race has been run, the racers have been identified, but now we face a totally new challenge. There is a tidal wave of data coming from that finish line. How on earth do we capture it all? And I'm not kidding, this is a huge problem. A modern mass spec is so unbelievably sensitive, it can see tens of thousands of different proteins in a single go. It's physically impossible for it to do that second lap analysis on every single one. It would be overwhelmed. So the machine needs a strategy. It has to decide what to focus on. And that brings us to the 2 main strategies for snapping that finish line photo, DDA and DI. These are 2 completely different philosophies for how the machine should collect all that precious data. So here's the difference. Think of DDA as a sports photographer. Focus only on the stars. It tells the machine just look for the biggest, most intense signals, the front runners, and get really detailed shots of them. But DII is different. It's like setting up a camera with a super wide-angle lens. It tells the machine forget picking and choosing, try to get a fragment snapshot of everything that crosses the finish line. You get a more complete picture, but the data is way more complex to sort out later. Okay, so we have all of this incredible data, masses, intensities, fragment patterns, you name it. But we have to put it somewhere, right? And because it's so incredibly complicated, you need special digital file formats just to keep it all organized. Usually, you're going to run into 2 main types. First is the raw file. This comes straight off the machine. It's kind of like the proprietary raw file from a digital camera. It has all the data, but it only really works with that manufacturer's software. And then you have MZML. This is the game changer. It's an open, universal format. It's like the PDF of the proteomics world. And it's fantastic for science because it means a researcher in Tokyo can easily share and compare data with a researcher in Toronto, no matter what machine they're using. And just like that, it's done. Think about what we just did. We started with a single drop of liquid, this complex, invisible soup of proteins. We gave them a ticket to ride. We raced them, we identified them by their broken pieces, and we captured a detailed photo finish. The great molecular race is over, and what we're left with is a map of that sample's proteome. This is so much more than just cool technology. This is about seeing the actual engines of our cells, seeing what changes when things go wrong, when disease takes hold. And that leaves us with one final, incredible question. Now that we have this power, this ability to map our own inner universe, what's next? What diseases are we finally going to understand and cure?